We do this all the time. Is it going to rain? Is my train going to be on time? We're constantly playing the odds. But what about an AI? How does it deal with uncertainty? How can it possibly make a smart bet when it doesn't have all the facts?
Well, for an AI, the world is just this chaotic flood of messy, incomplete data. To do anything useful, it can't just be guessing. It needs some kind of system, right? A way to manage what it thinks is true about the world and, crucially, to update those beliefs whenever new information comes in.
And that's exactly what we're going to dig into today. We are pulling back the curtain on one of the most powerful tools out there for this kind of thinking, something called a Bayesian network.
So here's the game plan. First, we're going to look at just how huge the problem is, why trying to model the real world is so tough. Then, we'll talk about a really clever shortcut that makes it all manageable. After that, we'll see how that shortcut becomes this blueprint for beliefs, learn how to actually read one of these maps, and then, finally, see it all come to life, powering the kind of AI that's already all around you.
All right, let's dive right in with the big problem. Why is it so ridiculously hard for a computer to reason about something that seems simple? Like, is it going to rain? So the most obvious way to do this, the brute force way, is to build what's called a joint probability distribution. Just picture a massive, massive table that lists out every single possible combination of things in the world, like every possible outcome. Rain and traffic, sun and no traffic, rain and no traffic. You get the idea. And for each and every one of those combinations, you assign a probability.
Sounds good in theory, right? But in the real world, this table doesn't just get big, it explodes. It grows exponentially. And this is a super famous problem in AI and computer science. They call it the curse of dimensionality.
And just look at this. See how fast it gets completely out of control? If you have just 3 simple yes or no variables, you've got 8 rows in your table. Okay, fine, manageable. But what happens when you jump to just 20 variables? Boom, you're looking at over 1 million rows. So yeah, this whole brute force thing, it's a non-starter. We desperately need a smarter way to do this.
And listen, it's not just about finding a hard drive big enough to store the table. The real killer is the data. To fill out that 1,000,000-row table with numbers that are actually accurate, you would need an insane amount of data to learn from. It's not practical. At all.
Okay, so if that's the problem, what's the solution? Well, it turns out it comes from a really elegant, almost simple observation about how the real world is put together.
And here's the key idea. In the real world, not everything is directly connected to everything else. The fact that I might have a toothache today has absolutely zero effect on the weather in Tokyo. And this simple fact, this idea of independence, that's our escape hatch. That's how we get around that massive explosion of possibilities.
More specifically, we're going to lean on this really powerful concept called conditional independence. What that means is you can have 2 things that seem related, but as soon as you know about some third thing in the middle, they suddenly become unrelated.
See, total absolute independence, like my toothache and the weather, that's actually pretty rare in the kinds of complex systems we want to model. But conditional independence, that stuff is everywhere. Think about it. A fire alarm isn't directly triggered by a fire. It's triggered by smoke. So if you already know there's smoke, finding out that there's also a fire doesn't actually tell you anything new about whether the alarm is going to go off. The smoke is the key.
Let's use a super simple example. You see someone carrying an umbrella, and maybe your mind jumps to, traffic's going to be bad. But hold on, why? The umbrella doesn't cause the traffic. They're both caused by a third thing, rain. So if you look out the window and you can see for a fact that it's pouring down rain, then seeing someone with an umbrella tells you absolutely nothing new about the traffic. Once you know it's raining, the umbrella and the traffic become independent of each other.
And this is where Bayesian networks finally enter the picture. They are the perfect tool designed to elegantly map out all of these independence relationships.
So what is a Bayesian network? Think of it like a blueprint for beliefs. It's basically a map, a visual diagram of cause and effect that shows you exactly what influences what. And the parts are super simple. Each circle, or node, is just a variable, something like rain or traffic. The arrows show direct influence. An arrow going from rain to traffic means exactly what you'd expect. Rain directly affects traffic. And here's a key point. The lack of an arrow is just as important. It's telling you that 2 things are independent.
Now here's where the magic really happens. This visual map, this blueprint, translates directly into much, much simpler math. Instead of a giant formula where everything is connected to everything else, we can break it down. We only need to care about the direct parents of a node.
So the probability of someone carrying an umbrella? It only depends on its direct parent, which is rain. It doesn't depend on traffic at all. This just slashes the number of calculations we have to do.
And that simplification isn't just a neat trick. It has huge consequences. Look, for a tiny little problem with just 5 variables, we've already chopped down the number of probabilities we need to store by almost 40%. Now scale that up. Imagine a network with hundreds or thousands of variables. The savings are just astronomical. This is the breakthrough that actually makes probabilistic AI possible in the real world.
Okay, so we've got our map. Now we need to learn how to read it. And figuring out how information or influence flows through this thing, it's the whole point. But it's not always as simple as just following the arrows.
How you read this map really comes down to 2 things: the specific pattern of the arrows and what you already know for a fact, what we call the evidence. Really, it all boils down to 3 key structures. The first 2, a causal chain and a common cause, are pretty intuitive. Information flows right through them, unless you observe the variable in the middle. Knowing that middle piece of information actually blocks the flow. But then there's the third one, the V structure. This one is the weird one. It behaves in the complete opposite way, and it's where things get really interesting and a little counterintuitive.
Yeah, this V structure gives rise to this really fascinating phenomenon known as the explaining away effect.
This example nails it. Let's say heavy traffic can be caused by 2 separate things: rain or a big ball game. Now, normally, rain and ball games have nothing to do with each other. They're independent. But the moment you observe the effect, the moment you see that there is heavy traffic, those 2 causes suddenly become linked in your mind. If you then get new info that it is, in fact, raining heavily, your belief that a ball game is the cause of the traffic plummets. Why? Because the rain explains away the traffic. You don't need the other explanation anymore.
All right, let's bring this all home. How does this elegant blueprint for beliefs actually power an AI in the real world?
We can look at a classic AI problem, the Ghostbusters example. You have this little agent, and its job is to find a ghost that's hiding somewhere on a grid. The catch is, it can't see the ghost directly. All it gets are these fuzzy, unreliable sensor readings from nearby squares.
And here is the beautiful payoff. The agent starts off clueless, right? Its prior belief is basically a shrug. The ghost could be anywhere. But the second it gets a new piece of data, a sensor reading, that's our evidence, it feeds that into its internal Bayesian network, and bam! It instantly updates its entire model of the world. The probabilities all shift, and it forms a new, much smarter, posterior belief about where that ghost is likely hiding. And this cycle, this constant process of taking in new evidence and updating your beliefs, that is the absolute heart of probabilistic AI. It's the same logic that helps a doctor work from a list of symptoms to a diagnosis, or how your email filter looks at the words in a message and decides, yep, this is probably spam. So what Bayesian networks really give us is this incredibly powerful framework for dealing with uncertainty, all by modeling the underlying structure of cause and effect. And it kind of leaves you with this big, exciting question, doesn't it? If we can keep getting better at drawing these causal blueprints for the world around us, what are the limits? What problems today seem impossible to understand or even predict that might one day be within our grasp?